start formally now. And the goal of today's lecture is to cover the existence of coarse moduli spaces. This is sort of the second lecture of this two-part sequence on the geometry of Deligne-Mumford stacks, where, to remind you, last time we did two things concerning the geometry of Deligne-Mumford stacks. We discussed quasi-coherent sheaves on Deligne-Mumford stacks, and then we also covered the local structure theorem of Deligne-Mumford stacks. And then we're going to use this today with the goal of establishing what's known as the Kilmore Theorem, which I have up here, that any separated Deligne-Mumford stack admits a coarse moduli space where X is a separated algebraic space. So we need to define what this means, and we'll do that today. And we'll prove the theorem. But I'd like always, I'd like to give a quick recap. I'm not going to really review quasi-coherent sheaves because we will use the structure sheaf today, but that's all. But we will use in a fundamental way the local structure theorem for Deligne-Mumford stacks. So let me just quickly recall what that is. This was the theorem that we established last time, that if you have a separated Deligne-Mumford stack and a geometric point, so a point defined over an algebraically closed field K, and then there's a morphism that's affine n étal from a quotient stack of the action of the stabilizer group scheme on an affine scheme, and it's affine n étal, and moreover it induces an isomorphism of stabilizer groups at the given preimage W of X. Right, and so yeah, this is right. That's about all I'll say for review. We'll use this theorem later, but I want to get to the core content on coarse moduli spaces, and I think I should begin with a definition. So we define that a map, a morphism, X to Y, X to X is, so in this here, X here is an algebraic stack, and this is an algebraic space. We define this to be a coarse moduli space. Which we'll abbreviate by CMS if, well, the following two conditions hold. First is that you need for all geometric points, so for all algebraically closed field, you need that the natural map, that if I take the k-value points of the stack, this is a groupoid, and so I could take the underlying set of equivalence classes of objects. And then that maps to the k points of the algebraic space. And I want this to be bijective. And so just this notation here means this is the isomorphism classes of objects in the groupoid. Right, and we're requiring that this map of sets be a bijection for all algebraically closed field K. And the second property is a uniqueness, well, ensures uniqueness, is that this map pi is universal for maps to algebraic spaces. Right, and maybe let me just spell out exactly what that means. That is, in other words, if here I have my morphism pi to X, and if I have any other morphism Y, where this is also an algebraic space, then there's a unique map. Right, so yeah, this is the definition, and sort of the reason why we care is we sort of view the coarse moduli space X as the closest approximation to the stack X, which is an algebraic space. And so somehow there's this like trade-off here. So we sort of sacrifice, like, you know, the stack X has universal properties. Like for instance, you know, there exists a universal family. Yeah, for instance, if X is the moduli space of is MG the moduli stack of smooth curves, you have a universal family. But we sort of we trade this off to get an object X, which is more familiar. Well, it's an algebraic space, and ideally, X is projective. And so the end goal is to show that your coarse moduli space is projective, at least in the context of MG bar, and having a coarse moduli space which is an algebraic space is the first step. Right, and well, and the reason, yeah, I mean, maybe you ask, it's a fair question. I think it's already come up. Why do we even care? I mean, if the stack, sometimes most questions often are best answered on the stack itself, because but the point here is we associate a more familiar object, like hopefully that's projective, and then we have more tools because we have a whole toolkit of projective geometry at our disposal, and you can then study, you know, the projective variety X and then infer properties about the stack if you want. Anyway, that's our goal. And the strategy is actually very clear how we're going to prove this. So our strategy to show the existence of a coarse moduli space. Well, it's really a two-part case that you handle. First, you handle the special case where that if X is a quotient of an affine scheme mod a finite group, here G is a finite, then you need to show that the morphism to the spectrum of the invariance is a coarse moduli space. And we will do this. We'll take yeah, that's one of the fundamental results from today. And then the second part is then to reduce to the special case. So then you use the local structure where now you have an arbitrary, you know, Deligne-Mumford stack, and the local structure theorem implies that there's, you know, a nice affine and étale cover. And this one, by the special case, has a coarse moduli space. And then the goal is to sort of glue these in the étale topology to construct X. All right, that's the strategy. Any questions on that?
Yes. So why isn't it a scheme?
Sorry?
So, I mean, so for the special case, the coarse moduli space is a scheme, right?
Yeah, in the special case, it's even an affine scheme.
And then we glue it together using étale topology. Why don't we get a scheme?
Oh, because we're going to glue under an étale equivalence relation, and we don't know much more about the properties. Is that yeah, we're just going to glue an étale equivalence relation, and it gives us an algebraic space because we're gluing the étale topology, not the Zariski topology. And moreover, maybe I should point out that in this definition, you know, note that property 2 implies that the coarse moduli space is unique. And in the special case where you start with an algebraic stack that is an algebraic space, the coarse moduli space is an isomorphism. So in general, like you can't hope for better. In general, yeah, an algebraic space is the best you can hope for to have such a general result. Right, that's a good question.
Thank you.
Okay, so moving on, and let me, so we have this, I recalled in the top, the definition of a coarse moduli space. These, just these two properties, but in practice, these conditions alone are actually not always sufficient for your purposes. In practice, we desire stronger properties. So for us, if X is a separated DM stack, we will construct a coarse moduli space satisfying additional properties. So first is that it's going to be stable under flat base change. Two is that the push forward of the structure sheaf is the structure sheaf. And that the map itself is proper. So maybe I should emphasize, in particular, it's separated. And then, and it's also sort of bijective. The definition implies that it's bijective on geometric points, and in our case, it's even going to be a universal homeomorphism. Wait, what that means is, like, for instance, that implies that the induced map on the topological space maps bijectively to the topological space of the algebraic space.
What do you mean in part A, Jarod?
That if you base change by a flat, if you take an algebraic space X prime and a flat morphism, and then you take the Cartesian product, that this too should be a coarse moduli space. Yeah.
Okay, thank you.
When I make precise statements later, I think I'm clear. Right. So I just sort of wanted to say that, yeah, like, well, one, it's not even clear what this is, that this is the best definition of a coarse moduli space, because in practice, you do want more conditions. And maybe I should point out that in these conditions here is that actually A implies B. We first note that, you know, like if you have, just let's think about what the universal property of a coarse moduli space implies in the setting that you take maps to A1. What this implies, a unique map here shows that the global sections of are equal. Because maps to A1, even for an algebraic stack, correspond to global sections. And but that's not enough just to conclude that the push forward of the structure sheaf is equal to the structure sheaf. You need to know that if you take an étal base change, that because this is also a coarse moduli space, we get that the global sections, that if I take the global sections of X prime of OX prime, which this is equal to, by definition, to the global sections of X prime of the push forward of OX. Or maybe I should really write, this is, you know, the push forward, this is in the étal topology. So this is evaluating at this étal map. And we know that, on the other hand, this is equal to X prime OX prime. And this is exactly the statement that OX, the natural map, is a bijection, is an isomorphism of sheaves. And And another useful property that will show up repeatedly is that you can construct coarse moduli spaces by descent, or you can check that both of these defining properties of a coarse moduli space hold after a tal or even flat base change. So let's let this just be a morphism. Here, again, this is an algebraic stack and an algebraic space. And if, suppose we have in a tau cover, it could even be FPPF, such that the base changes, such that if you take the base change of x cross x over xi, mapping to xi is a coarse moduli space, then x to x is. And the reason this holds is just descent. You know, the first property is just a condition on like geometric fibers, so that holds after a tau, that can be checked on a tau base change. And the second property as well, you need to use a tau descent for morphisms. If you haven't, yeah. But I'll leave the details to you, right? But we'll use this. Any questions on these first properties?
Because the definition uniquely classifies a coarse mod, pins down one, I don't understand what you mean by like, maybe this is not the right definition, like we need more properties, because if those properties hold, don't we already have them because there's a unique one?
Oh, if you start with a separated Deligne-Mumford stack and you have a coarse moduli space, then it will satisfy all these other properties. But like really, like you can imagine more general algebraic stacks or Deligne-Mumford stacks that are not separated. And then there are some cases where they have coarse moduli spaces, but they don't satisfy these further conditions. And then there's even examples of Deligne-Mumford stacks that don't have coarse moduli spaces at all.
So is MG separated?
Is what separated?
MG, the stack MG.
And oh, right, MG is separated. That's something that, right, this is a good point. Well, okay, I don't have, maybe let me return to MG later. Well, okay, no, you asked. We actually have enough now to show that MG is separated. So the Kilmore Theorem will apply to MG once we show that. And so this will be our ticket to show the existence of a coarse moduli space for MG and MG bar. But we do need to, but I'm sort of putting off the separatedness until we discuss stable reduction because the ideas are similar.
Okay.
Are there situations where Artin stacks or algebraic stacks have coarse moduli spaces?
Yeah, that's a good question. Like, so for instance, like you could view the Picard stack, for instance, like if you're looking at the class of like the stack parameterizing line bundles on a given projective variety, where you include the data of the automorphisms, and then this has a GM stabilizer because the automorphism group of any line bundle is GM. So you have a stack that has a GM stabilizer at every point, and this does have a coarse moduli space, which is the Picard scheme. And this is even, you know, a particularly nice coarse moduli space that in that case the map's not separated, but it's called a GM gerb, meaning that all the fibers are just EGMs and they're very nicely.
That's okay. Thank you.
Or more generally, like if you look at the moduli stable vector bundles, the map from the stack to it does have a coarse moduli space. It's just rigidifying these GMs.
Thank you.
Okay, so I think the next thing I want to do is cover the existence of a coarse moduli space in the special case of finite groups. And this is sort of a classical story, but I want to spell it out again. And so so we're looking, here's this, the setup here is G is a finite group. Oh, that was the eraser. G is a finite group acting on an affine scheme. And the fundamental construction is this ring of invariants, AG. And there's nothing tricky going on because G is an honest, discrete, finite group. So therefore it acts via automorphisms on the ring A. And it makes sense to talk about the invariant ring as all elements, all functions in A that are invariant under the group. Right. And our first lemma, and the spectrum of the invariance is going to be, our quotient in this case is going to be the coarse moduli space in this case. And so we're after understanding its properties, which is what these two basic lemmas establish. So in this first lemma, we're fixing an Ethereal ring, and we assume that if A is finitely generated over R, then this morphism is finite, and the invariant ring itself is finitely generated. And this is sort of an important point here that, like with these hypotheses, A itself is an Ethereal ring, but we're defining the subring of an Ethereal ring, and a priori it's just like it might not be an Ethereal. It's something that you need to check. In this case, because G is finite, yeah, we have more at our disposal. In general, when G is arbitrary, this is like Hilbert's 14th problem. And when G is not reductive, the invariant ring is not always finitely generated. But this is sort of an easy case because G is finite. So yeah, let's prove this.
Sorry, I suppose here G acts by R algebra morphism in this lemma.
Yes, AG has the structure, yes. I'm not sure what the question is. Yeah, like the structure.
In this this lemma to be true, G should act by R algebra homomorphism.
Oh, okay. Yes, exactly. Yeah. That's right. And now I see the point. Yeah. G acts. Let me just add this here. In this context, G acts via R algebra homomorphisms on A, right? Or in other words, the map from the spectrum of A to the spectrum of, that ensures that the map from the spectrum of A to the spectrum of R is G invariant. So everything lives over spec R. Yeah, thank you for that clarification. Okay, so to get started, the first thing we just realized is that AG to A is integral. And because if you take an element of A, then you can just find a monic polynomial. I just take the product over all group elements of X minus GA. And then because I'm taking the product over all elements, all these coefficients are actually going to be invariant. So this is a monic polynomial with A as a root. So that handles the integrality. And so we're in the setting where R maps to AG, maps to A. And we know that this map is finitely generated. But that ensures that AG to A is also finitely generated. I mean, A is a finitely generated algebra over its invariance. And because it's also integral, that implies that this map is actually finite. So this map is finite homomorphism of rings. And now we just use some commutative algebra. This is a T.M. McDonald, that because R is Noetherian, any subalgebra of a finitely generated one, such that exactly with these hypotheses, such that A is finite over it, is then plus AG is finitely generated as an R algebra. Okay, and now turning to the second lemma, what we this is establishing properties of the invariance with respect to base change. So I'm in the same setting as over here, and now I take an arbitrary ring map, AG to B, then G acts on this fiber product, and we have this sort of diagram here that we'd like to understand, right? This is just this square is Cartesian by definition. This map here is G equivariant. This map is G invariant. This map is G invariant. And so there's two properties that we'll use. First is that if this map is flat, then B coincides with the invariance of the fiber product. And in general, it's not always an isomorphism, but this morphism is at least an integral universal homeomorphism. And but yeah, and these properties actually aren't hard. I'll do the first one. We just realized that the invariant rings, sits as the equalizer of this diagram, where one map is sort of the diagonal inclusion, and the other map is given by multiplying by elements of G. And then because tensoring is exact, oh, nope, I got that wrong. That implies that B sits inside A tensor AG B where this is A tensor AGB. Since this is exactly telling us that the invariance of this guy is B, right? And then the second one I'll leave as an exercise. Okay, any questions on these lemmas? Okay, so now we get to the special case. So this is our theorem in the special case of a quotient of an affine by finite group. So we need to show that this morphism is a coarse moduli space, and that satisfies these three other properties. And what we already know is highlighted here in red, that we know that this inclusion from the invariance to the ring is a finite extension. And we know that the invariant ring is finitely generated over R. So in other words, we already showed one. The challenge is showing that it's a coarse moduli space. And so so I'm going to break this into a couple steps. The first step is to show that the map is a proper universal homeomorphism. And this then implies that pi is bijective on geometric points. So to do this, well, we consider we have A maps to the quotient stack, and this maps to the invariance. So we have this commutative diagram, and we know because G is finite, this morphism is finite. And we've already showed that this map is finite. And by construction, because the invariance is a subalgebra of A, this is schematically dominant. And in particular, therefore, it's surjective. And so because it's surjective, you can then infer that this map is proper. So we get that essentially for free. And what we need to show is that pi, this map pi, is injective on geometric points. Oh yeah, because we already know this map is surjective. So it's already, you can use this to conclude that it's surjective on geometric points. So we just need to show it's injective. And for this, everything comes down to geometric points. So we can assume that R is just K is algebraically closed. And we're going to let X and X prime in spec A be 2 points, closed points, with distinct orbits. Right, but because the orbits are distinct, they don't intersect at all. They have empty intersection, and these are the orbits are subvarieties of spec A. And you can always, whenever you have 2 disjoint closed subschemes of an affine scheme, you can always find a function that is 0 on one and constant on the other. So there exists a function f in A such that f restricts to 1 on this orbit and 0 on the other orbit. And then we sort of do the same trick we always do with finite groups, is you average over the group elements to force it to be invariant. So then this is an invariant polynomial with the same property. And the whole point is that it's an invariant polynomial. And this invariant f prime is a function on the invariant ring. So what that tells you is that the images are different because we have a function that separates them. Okay, so since it's injective. It's actually, therefore, pi is bijective on geometric points. And since pi is proper, the image of a closed set is closed. And so the inverse map is also continuous. So that this implies that pi is a homeomorphism. And then, but we need to show it's a universal homeomorphism. And so we now need to use these base change properties. So if you take an extension like this, let's just go back to see what we had written over here. We had sort of this nice diagram. That if I just so we're in the setup. We have this diagram, and in this diagram, what do we know? We know that that this map is a homeomorphism because this is the G invariance, and the lemma told us that this was a homeomorphism, and so that implies that this is also a homeomorphism, which implies that this is a universal homeomorphism. Right, so that was, so then we now know that handles part 2. Right, any questions before I move on to the next part of the proof?
Yes, but how do you know that pi is bijective? I mean, it is surjective, but on geometric points, right?
Yeah, it's I showed it's injective on geometric points. And I think that maybe the point was that this map from spec A to spec AG, we know it's both finite and dominant. So that map's surjective. And that allowed us to conclude that this map was surjective. And therefore that it's surjective on geometric points.
Of course. Sorry. Thank you.
No problem. Okay. So so moving on. So like, okay, so we've done now step 1 and step 2, and we've established one of the 2 defining properties of a coarse moduli space. We now are after the other defining property, namely that this map is universal, satisfies this universal property. This is, yeah, maybe the harder part of the argument, but and maybe before getting to this, I should just remark that, yeah, if Y is affine, then, right, then we have a morphism. If Y is affine, then we have a morphism from this global functions on Y to the global functions on X. But this is identified with the global functions of the algebraic space X. And so this map here defines X to Y because both X and Y are affine. So in the affine, when Y is affine is the easy case. So we need to argue, let's see. So let's start with the uniqueness. So let's suppose, let's suppose we have a diagram where we have X and we have Y, and suppose we have 2 maps, H1 and H2. Right, and so then we take, let E be the equalizer of these 2 maps. So precisely, it's given by this fiber product over the diagonal of Y. But sort of then so E sits inside X. And we know it's a monomorphism. And sort of by definition of the equalizer, we know that this factors. So we have this factorization by the definition of the equalizer, because we know, that after composition with this coarse moduli space, then these maps are equal, right? And we know because Y is an algebraic space, the diagonal is both a monomorphism and locally a finite type. So that implies the same thing for the equalizer. Okay, so what our upshot is that, okay, what do we know? Oh, we know that, that the goal is to show that E is equal to X, that the map from E to X is an isomorphism, and we know it's a monomorphism and locally a finite type. But this map to X is, we know it's proper and schematically dominant. And therefore, we know the same thing about the map from E to X. It's also proper and schematically dominant. So we have so wrapping up all of the properties. So E to X is, so I guess the upshot, it's a monomorphism. It's locally finite type. It's proper, and it's schematically dominant. Meaning that the inclusion the inclusion from the structure sheaf to the push forward of the other structure sheaf is injective. And if you think about these conditions, that just these three, the first 3 imply that it's a closed immersion. This isn't, this is just a standard. In fact, that's not very hard to show. But now, because it's schematically dominant, that implies that it's actually an isomorphism. So we win. Okay, and now, okay, so now we turn to the existence. Let's see. So I want to claim that the question of existence is a tau local on Y. In other words, we're in this setting on the left-hand side where we're given this map phi to Y from X to Y, and we want to construct a unique map from X to Y. And the point is, because we already know that that extensions are if the extension exists, it's unique. That allows us to apply a tau descent in order to make the question a tau local. So the reason for this is true is a tau descent and the universal property. Right. The point is that if I know after in a tau map that I have a morphism from X to Y prime, then I can apply descent to get the proper map. All right. Yeah, there are a lot of ingredients to this proof, but so the upshot here was that since it's a tau local, we can assume that Y is like the local ring in the tau topology. So we can assume that wait, give me 1 second. I'm slightly confused. Yeah, something. Oh, actually, yeah. Oh, sorry. Yeah, sorry. I don't want to show that it's a tau local on Y. It's a tau local on X. Yeah, that was confusing. The point. Let me. Yeah, because that's the point was if you have in a tau cover of X and you have these morphisms, then on the double base change by the uniqueness that the compositions agree, which then gives you by a tau descent the map from X to Y. So a tau local on X, that's what we're using, and that's what we're going to use. And so that means that because it's a tau local, we can assume that X, which is the spectrum of the invariant ring, is Henselian, even strictly Henselian. And we can also assume that Y is quasi-compact. Right. The reason for this is that X itself is quasi-compact, and therefore the map from X to Y factors through a quasi-compact open in Y, and so we just replace it by that, and so we can assume that everything in the picture is quasi-compact. And so maybe I should move on to this page here. So where are we here? Okay. So we have these reductions that AG is strictly Henselian, and we know that Y is quasi-compact. And we're in the setup that we have X, we're given some map to Y, and we want to construct a map like this. And since Y is quasi-compact, we can choose Y prime affine and in a tau presentation. Okay, and I think I need a little more space. And so if I take the base change, let's just complete this diagram. Let's take X prime here. This is a fiber product. And we also know that we have a cover here, spec A, and we have this morphism. And let's just take this to be the base change. So this is our diagram. And because, okay, we know that this map is finite, and this is Henselian. So that implies that this is also Henselian. So in fact, the only two properties that we'll be using about Henselian rings is that it's stable under finite extensions, and that any étale cover of a strictly Henselian thing has a section. Right. So in this picture, this is étale. This is étale. And right. Oh yeah. Here's the point. Right. So because spec A is Henselian, and we have an étale morphism, strictly Henselian even, then there's a section S. Which then descends to a section of this map. And now, okay, where are we? Y prime is affine. What do we know here? So we're going to use the, okay, since Y prime is affine, and there exists a map like this. Sorry, I'm getting confused here. This is not as tricky as I'm making it seem. Oh, okay. Yeah, I think I got it now. Sorry. Okay, let me back up. The point is that I've used the Henselian property, and because I have this étale extension here, there's a section. So there's a section here. So under the section, X maps to X prime, maps to Y prime. And now Y prime is affine. And we already know the affine case that there then exists a map like this. A unique map like this, and therefore we get the composition to Y. All right, that wraps up the proof.
Why did the section S descend here? Do you need to know something like its G invariant?
Yeah, you need to show it's G invariant. I think the point here is everything. Yeah, I think you need to. Yeah, I'm going to use a similar argument later. I mean, it's an extension of an étale representable map. So the section itself is an open immersion. And in fact, if Y prime to Y is separated, then the section is also a closed immersion. So you can think about this as just a component of the other one. So you get sort of the G invariance for free, if I'm not mistaken. Let's return to that maybe later. That's a good question. Yeah, there's a lot of details you can ask. Yeah, details about every single aspect of this argument. Yeah, let's return to that. Okay. So all right. So now that we know the affine case, let me just sort of repeat our strategy. You know, we're after a coarse moduli space for X. I think I need, yeah. So our strategy is to construct a coarse moduli for X. We use the local structure result to find this étale map. Here we have a coarse moduli space. And the way let's call this W. And so the natural thing to do is to sort of consider this base change here, W over W, yeah. And because this map is also affine, this itself is going to be spectrum, like an affine scheme mod the stabilizer. So here you also have a coarse moduli space. And we have two maps. And these are given by the universal property of coarse moduli spaces. And what we need to know is that this is an étal equivalence relation. Because once you do that, we can then take the quotient as an algebraic space and argue that that's the coarse moduli space for the stack X. And so the central question here is, so if we have an affine morphism of affine schemes that's G equivariant and étal, when is the quotient map étal? And maybe okay, and I'm going to give a precise statement in a moment, but let's just argue maybe heuristically to try to see what properties should we impose. And let's just assume for this heuristic argument that everything is over an algebraically closed field, and let's let X be in spec A. And the fact, this takes work to show, and the argument actually will not be using this fact. The argument it will be, in fact, a little bit simpler, is that if I take the invariance of A, if I take the completion of A at X, and then the stabilizer group will act on that is identified with the invariance of A completed of AG along at the image of X. And so if F is étal at X, what that tells you is that their completions of the local rings are isomorphic. So in this context, like A hat mapping to B hat, where B hat is the completion of B at the image of X, that's an isomorphism. And we want to know, when is this quotient map? Let's call that F bar. Then F bar is étal at the image. Well, if and only if the induced map of its local ring, so the completion AG completed mapping to BG completed is bijective. But by this fact, we have identifications. And so that tells us that what we need is that the invariance of the completion of A at the stabilizer of X should be equal to the invariance of B completed, the invariance with respect to the stabilizer of the image of X. And so the upshot here is, if these stabilizer groups are identified, we win. Because the A hat is equal to B hat, and if the groups are equal, then their invariants are equal, and we get that the map on completion on the quotients are equal, and that's étal. So it's a sort of a heuristic argument to expect that, if the stabilizers are equal, étalness should descend to the quotients. Right, and that's the content of the next proposition, but I'm going to state it and prove it quite differently. Right, so the statement here is, it's exactly sort of in this setup that we have a finite group, we have a G equivariant map, and we have these two key assumptions here, that the map is étal and it induces an isomorphism that stabilizers. Then the statement, because this is of a local nature, then the statement is that that after shrinking spec AG, there's an open subscheme W, even affine, such that the induced map from W is a tau, and the outer square here is Cartesian. And in fact, in the context that we're going to use it, is in fact we have more properties. So maybe let me just is that if in addition these two properties hold at all closed points, then that we get globally that the map on quotients is a tau. So then we get that this map is a tau and it's Cartesian. Okay, so let me sketch this proof, because the proof is going to be similar to the other one. It's just going to be sort of a reduction using properties of Snellian rings and a tau dissonance. And so like in the last case, I have, I want to argue that the question is a tau local around the image of Y. So here maybe we have our points X mapping to Y. And the question is a tau local. Maybe since I'm taking longer than I thought, maybe I'll skip that step, but it is a tau local. And what that tells us is that BG, we can assume that this is strictly Henselian. Right. And so, right, we're in the context, let me use this diagram again. So here's the strategy. So we know, we're assuming now that this is strictly Henselian. So that implies that B itself, because it's finite over its invariance, is also Henselian. And then, because this is a similar argument before, we're assuming that this map is a tau. And because B is Henselian, you have a section. And then you argue that if this section is G invariant. In this case, I think it's even easier than the last case, because this section is an open and closed immersion. And now, well, what are we trying to show? Well, we want to show that we can shrink spec AG Zariski locally so that the induced map on quotients is a tau and the diagram is Cartesian. But this tells us what we can do, because the S is an open and closed immersion. This is an open and closed. So its image, if I just take like the image of S, this is an open and closed substack that's isomorphic to spec B mod G. And then this has tautologically the quotient, which is PG. And this map is not only a tau, it's an isomorphism. And so a tau locally, we handle it. Is this okay? It's kind of a sneaky proof, because maybe all of the details are on the reduction to the Henselian case.
Wait, I'm sorry, that was a little fast. Can you say that one more time? Like, can you like go through, I guess, like,
yeah, sure,
with this diagram one more time? Thanks.
Right. Let me try that. So the first step of the argument is to assume that that BG that the spectrum of BG is strictly Henselian. And in other words, that the question is a tau local here. Yeah, this argument, it's not that hard. I should point that, like, the fact that it's a tau local is not that hard. That's standard descent theory. But then you do need to know some properties of strictly Henselian rings, and you need to know that basically the same way that you go from like in the scheme case about properties of the local ring in the Zariski topology to then spreading it out to an actual open neighborhood is of the same flavor here. So you need to know that if it holds for if you can argue over the strict Henselian, then you can actually argue over an honest, and you can spread it out to an honest to tau cover and then use descent. But assuming that we're okay with this reduction, that BG is strictly Henselian, then then we're sort of in it's sort of in a much easier situation because B is finite over BG, so spec B is Henselian, and I'm given in a tau spec A that is a tau over spec B, and so it's a tau cover over a strictly Henselian ring. Therefore, there's a section. And then we use this section in order to identify an open and closed substack of spec A mod G that's isomorphic to spec B mod G. And this is the open that we use to shrink in order to ensure that the map on quotients is a tau and the diagram is Cartesian.
Okay, thanks. I think hearing it one more time made it make more sense.
Yeah, there's a lot to it. All right, so now I want to go. So we finished all the ingredients we need, and I want to sort of wrap up the proof of the Kilmore theorem. So here I have a lot on this page here, but the three things on the right-hand side we've already proven. What we're after is is on the left-hand side. This is what we're trying to prove. That if you have a Deligne-Mumford stack that's separated, then there exists a coarse moduli space with all of these additional properties. In particular, the coarse moduli space is separated. And there's, on the right-hand side, we have the three ingredients that will allow us to prove this quite easily. Basically, this here is the special case of a quotient stack. And these two will allow us to reduce to the special case. But let me spell that out in detail. Yeah, I think I'll finish at 12. Yeah, maybe I'll need another 10 minutes because I do want to wrap this up. And I think we have all the ingredients. So let's do it. Okay, so let's assume, okay, this was stated when S is an algebraic space, but you can reduce to this case, the case where S is affine. In fact, this reduction argument is along the same lines of the entire proof that I'm going to give now. So the reduction step should maybe be done after the entire proof. And now I argue that the question is Zariski local on X. Because if I can cover the stack with open substacks, and I have coarse moduli spaces for each of those opens, by the universality of coarse moduli spaces and the fact that induces an isomorphism on their underlying topologies, I can then glue them to form a global coarse moduli space. And the fact that our argument is showing that we can not only do it Zariski locally, but a tau local. And so it suffices. So what this means, it suffices to show that for a closed point, that there exists an open neighborhood of X with a coarse base. And so let's choose a representative of this point. A representative of X, and let's take it to be a geometric point, and then set G to be the stabilizer of this point. So it's a finite group. And the local structure theorem gives us this map that's a tau affine to X and a point W mapping to X. And we know that the automorphism group of W maps bijectively to the automorphism group of X. And so what the heart of this argument is showing, we need to show, let's call this condition star. So we need to show that this condition star holds also in a neighborhood of W. Or given that it holds for at a single point that induces an isomorphism of stabilizer groups, we want to know that it actually holds in an open neighborhood. And this is where the separatedness hypothesis is coming in. Right? This is so X separated. Well, what does that imply? It implies that the diagonal, by definition, is proper. Or in this case, it's because it's Deligne-Mumford, it's finite. And then if we base change by the diagonal again, we get the inertia stack. And so we know this map is finite. And so what we do is we consider sort of the map on relative, sort of the relative inertia map that you have the inertia of W over W. And this maps to the pullback of the inertia of X. Right, with this, no, that's a typo. Right, and now because this is the base change, right, this is the base change of Ix to X, and this map is finite, this map is finite. Okay. Let me discard this right-hand part now. But it actually turns out, this is sort of an amazing Cartesian diagram. Turns out that if you consider the fiber product here, that this square is Cartesian. So I should point out two things. First is that let me first spell out that what is this map really doing? This is like a relative map. This is a map of group schemes over W. And such that for like a fiber, such that for a point, a geometric point, the fiber is the induced map on automorphisms. So this is sort of the right map to study. And the second point is that this is a Cartesian diagram, which will help allow us to identify properties of this morphism of group schemes. The first is that note that W to X is affine. So that implies that this map, so affine maps are separated, and this map is representable, so this map is closed. It's a closed immersion. But it's also a tau and representable. And this implies that the diagonal is actually an open immersion. So this map is both closed and open. And so therefore this map is also closed and open. In other words, it's just a union of connected components. IW, the inertia of W, is just a union of connected components. And therefore its complement is also a union of connected components. In particular, it's closed. And so if we take this projection to be P1, take P1 to be the image take the image of under the complement. This is a closed subset. And because the inertia was finite over X, this map is finite. And so this is a closed subset of W. And it's precisely where the map W to X is not stabilizer preserving. And moreover, we're given a point, W, which we know it is stabilizer preserving at that point. So that, therefore, if we just throw away this whole closed subset, we arrange. So the upshot is that we can arrange that W to X is stabilizer preserving. And we can even arrange, because we just need to show there's an open around our, we could even arrange this map is surjective. Because it's a Zariski local question. All right, so now we're in a good shape. Yeah, and this was really where we used that one key hypothesis where that the stack is separated, or the inertia, really that the inertia is finite, in order to argue that you can shrink Zariski locally to ensure that it's stabilizer preserving everywhere. If you drop the separated condition, this fails and this argument fails, and the result is not even true. Right, so going back to the proof, now what we have is we have our stack. We have W, and we have a surjective, étale, affine morphism that's preserving stabilizer groups. And we have a coarse moduli space W, which is spec AG. And I'm gonna go to the groupoid level where I take this fiber product and this has a coarse moduli space. Again, this is just an affine mod, a group, the same group. And so this has a coarse moduli space R, and I have two maps. And now since W to X is stabilizer preserving at all points, so is these two projections from the stack R. And it's also étale and affine. So we're in the situation where that lemma told us that the two diagrams, the two squares are Cartesian. And that these maps, so we get that both of these maps are étale and both squares are Cartesian. So the upshot was that this induced map R to W, this map up is an étale groupoid of even affine schemes. In fact, to get the groupoid structure, you need to argue one more level, right? Because you need this inverse, you need this composition, but you have, because everything here is sort of was sort of by base change, and you have all of the arrows and this sort of simplicial stack you get from taking these base changes. You get the same thing by using the universality for maps in of course moduli spaces downstairs. That gives you the groupoid structure, and then the only thing you need to check, and I won't do this because I'm running out of time, is that the diagonal is a monomorphism. And since it's a monomorphism, we could take X to be the quotient. So that gives us X here, and we have a morphism. And then you just finish the proof using étale descent. Descent will give you this morphism, And then descent will also imply that this is Cartesian. And then we use the fact that coarse moduli spaces can be checked tau locally. So we get that this is a coarse moduli space. And you get you can check all the other properties too using descent. Maybe the one thing one thing to point out, maybe the one, y is x separated itself. And this just follows from the general fact that here you have, we know that this map is proper, and we know that the stack itself is separated. So you actually get that this is separated for free.